Hi guys, happy Monday, week number 3. I hope you had a restful weekend. I hope everybody's doing great. So it's Monday, which means another video from me. This one will be for chapter 4, biomechanics. And of course, I'm going to give you some feedback. I'm going to let you know or remind you what's due for this Sunday. Some updates, and then of course going over what we're covering this week, which is chapter 4. Okay, so I have my notes here. LO3 and LO4, I think you have already received your grades and your individual feedback. I'm very satisfied. You did very well. Congrats. Just remember, follow the instructions, the A's and B's and C's or whatever. Just make sure you're clear. Help me understand. Use proper grammar and syntax. Paragraphs, short sentences help me, so I can help you back. When you're using online resources or other resources in general, other than our textbook or even our textbook, please try to use your own words, because I can tell very easily through the software I'm using, and I'm checking if you are copying and pasting some parts. Okay, I've been very lenient with some of you. Just please use your own words. I've said that from the very beginning. I appreciate you looking further and looking online for web, sources. Amazing, awesome, great. If they are, as long as they are reliable. But please understand the material, comprehend what's going on, and use your own words in your answers. Okay, now I'm gonna go and share my screen. We're gonna go to Moodle. And all right, so this is week 3. I finished chapter 3, anatomy and kinesiology, last week because I didn't want to split it. And this week I'm only covering biomechanics. I wanted to start XPhys, but since it's going over most part of it in week 4, sorry, I'm just gonna do the whole thing next Monday. Now, what do we have for this week? LO5 is about chapter 3, anatomy and kinesiology. It's about bones, okay? And that's a quiz learning opportunity that is, I think it has 5 questions, and it's about bones, and all that information is in chapter 3, okay? And then you have a LO6, which is about chapter 4, which we're just about to go over, cover. Here, I'm going to give you some autonomy. I'm going to give you some freedom. Pick whatever you like. There are 3 case studies. Pick one and explain. The answers are in the book. Don't try to go be fancy. Just be very clear and show me you understood, and use your own words and answer all questions. Okay? 3 case studies. The answers are in the book. Okay? All right. What else? Oh yeah, week 3. So I think I told you about it. I was thinking about creating some synchronous meetings here and there. So we'll start this week. We'll do another in 3 weeks. So week 3, 6, 9, 12, and not the 15th week, which is the last one, but probably the finals week, because we don't have final. We're just gonna visit and talk. What's the meaning? This is Wednesday at 10 o'clock, okay? It's non-mandatory, right? But if you can make it, I'll give you 5 extra points. And the point of this synchronous meeting is actually meet live and talk about everything we've been doing. If you have any questions, concerns, feedback, ideas, and it's for 45 minutes. If we need the whole thing, we'll do the whole thing. If we don't, we don't. Okay. The Zoom meeting information is here, and again, it's for Wednesday at 10. Cool. I just want to do, I just want to see you. I just want to talk with you. That's it. If you can't make it and you still have questions, concerns tomorrow, as every Tuesday, I have office hours, and I'm going to be online for 4.5 hours starting at 8 o'clock in the morning. So you can log in. And again, we'll have another opportunity tomorrow to talk and another one on Wednesday. But on Wednesday, just our class. Okay? All right. I'm going back here. That's all I think I have for Moodle. I'm going to stop sharing this. And I'm going to start sharing our chapter 4. All right, biomechanics. Let me go here. Let me see if this works. Yes, I think it works. We're good to go. All right, biomechanics. We have a lot of material to cover, but again, this is not a course that I want you to go into like a depth that is like too much. I want you to understand basics, the basics, and you have kinesiology for this course. You also have analyzing human movement with me, most likely in your last semester. So I just want to go over the basics. Okay, biomechanics is a whole subdiscipline of exercise science, and we're just going to cover the whole thing, which is impossible, in one sitting. Okay, biomechanics. A word of Greek origin. Bio means life, mechanics has to do with physics, forces, analyzing forces, why we move the way we move, and how we move the way we move. Okay? Now, in all biomechanic courses, classes, we have to talk about Newton's 3 laws. Okay? And you see on the left column, we have those 3 laws: law of inertia, acceleration and reaction, and then we have linear movement, and then we have angular movement, which is rotational movement. And the second and the third column, they're pretty much the same thing. It's just the difference is in the second column, we're talking about linear movement, okay? And then it's just the same thing, but there's rotation happening. All right, so the law of inertia says that an object which is at rest will stay at rest, or an object that's moving will keep moving the way it's moving unless we apply an external force. Okay, so this will stay here, or if there was ice and there was no friction and you there was no friction and ice at all, just throw a pack, right? A pack will just keep moving until the end of time unless an external force, which in our case, if we do with a pack, would be friction from the ice and probably wind, right? Blowing the opposite way and so on and so forth. But if something is at rest or it's moving, the object is going to keep doing whatever it's doing unless we apply an external force. And if we go to the angular movement, the same thing, just a rotational. Torque, like you see, the word torque means rotational force, pretty much, okay? It's force when there's rotation. Acceleration, the linear acceleration of an object is produced by force, directly proportional to that force, and inversely proportional to the object mass. So F equals M times A. If we solve for A, right, it is F divided by M, which means what we just said. The acceleration will be proportional to the force and inversely proportional to the mass. So the higher the force, the higher the acceleration, but the bigger, the more the mass of the object. If you're trying to push something that has more mass, right, it will accelerate less if the force remains, of course, the same. I hope it makes sense. And again, The third law, I'm sure you've heard of it. For every force, there's an equal force at an opposite direction. And a great example that we're going to cover in another course, of course, for example, is the ground force reaction. Okay, so yeah, that's all I want you to remember from that, and we'll see its application in a little bit. Okay. Levels, 3 classes. That's important, and I want you to remember that. We have 3 players, as you can see: force, the vacuum, and the resistance. 3 players. Now, let's talk about the order. If the fulcrum is in the middle, then it's always a class 1 lever. Okay? Which means on one side we'll have the force, right? And on the other side we'll have the resistance. So when we talk about force or resistance, we usually, in this case, we talk about the weight and then the muscular force. Okay? All right. Here and here, so class 2, class 3, the fulcrum is on, it's not in the middle. When the force is on the other side of a class 2 lever, when the resistance is on the other side, we have a class 3 lever. What does it mean? Who cares? Well, in a class 2 lever, we have what's called mechanical advantage. Compared to class 3 that we don't have, we have a mechanical disadvantage. And in very simple words for this course and just for now, remember that for the same amount of weight, okay, which weight again is the resistance, in a class 2 lever, we need less force. So it's easier to move the same amount of resistance or weight. Why? Because of physics and of the way this is designed. So a class 2 lever again has a mechanical advantage. Class 3 lever has a mechanical disadvantage. You can go online and you can see many examples of tools and levers in the human body and see if it's a class 2 or a class 3 or even a class 1. Unfortunately, guess what? Most of our articulations are designed in a way and we move in a way that most of them are what? The human lever systems are shorter than our class 3. So far, so good. Okay. Scalar quantities and vector quantities. Again, we're not going to go into a lot of detail, but in vector quantities, remember that we care about magnitude, how much, about force we're talking about, for example, and also the direction. And you can see it here. Okay? So here, you see the direction of the force, and it's split into 2 forces. A lot of times when we have, the vector quantities, this is what we see, but what's actually happening, we'll have this, the force parallel, and then we'll have the force perpendicular. And when you combine these two, you get this one. What is this and who cares? This is here mainly for stability of this articulation. This is the one that shows the effort to move those 10 kilograms. I'll come back to that because it has to do with one of your laws and it has to do with one thing that I want to cover today, which is the sticking point. Okay, again, 2 forces. If we combine them, we get this one, but what's actually happening, we have 1 force here and 1 force here. Okay, F perpendicular, we are interested in this one because it shows the effort, and this one is here for stability of the joint. Here we have an example of a Smith machine, and we have an example of wasted pretty much effort. This is a vector resolution, as you can see. So we push up but the bar is going a little bit backwards. So we see that wasted muscular force because we're raising the bar in an angle Smith machine. And that's an application of what we talked about right now. All right, sticky point. I'm not gonna give the whole thing because I want you to study a little bit. If I see a lot of issues, of course, I'm gonna come in the next video and give feedback. All right, the 90-degree elbow, 45 and 135. Okay. We see here the direction of the force that comes through the muscle. We'll also said that it breaks down into two forces. The force, the parallel that we don't see here, okay, and the perpendicular. The perpendicular force, as I said before, we're interested into that because it shows the effort. And here, in all these three different angles, different positions, the moment arm here where the muscle attaches remains the same, this distance, right? But what changes is the effort that we need to move the same amount of weight, whatever, let's say it's 100 pounds, it doesn't even matter, right? But if you do a bicep curl, right, where does it feel heavier? Where? Think about it. Think about it. Do the movement. Think about it. Visualize it. It feels heavier somewhere around in the middle of the movement, right? One, here we have an issue of muscle geometry. And that muscle geometry changes throughout the range of motion that we talked about. And that affects the effort that we need to move the same amount of weight. So this is essential for you to understand. So as you can see here, the F perpendicular is 99.9, here's 79.9, and here's 79.9, which shows you that this specific angle, 90 degrees, in order to move the same amount of weight, no three, right, 100 pounds, it needs more effort. It feels heavier. It's not, it's 100 pounds. But because of muscle geometry and because it changes throughout the range of motion, at this point, you require more. And that's where I'm going to stop. I hope that's enough for now. What do we have here? Here you see pulleys, right? And we have here in this pulley in the whole circumference, D1 is equal to D2. Here D1 is smaller than D2. When we have D2, sorry, but what was it? Okay, sorry. All right, that was weird. When it's D2, because the moment arm, that's how it's called, is long air, moving the same amount of weight feels heavier. Why would we create something like this, kidney shape? Because it imitates what happens with the human articulations, okay? And we just proved that with a sticking point. So this is more functional, it's more realistic, it's closer to what happens in the human body. And that's why we create things like that. You will always see things like that, but this is more, again, it's closer to what happens in the human body. Make sense? So this is another application of physics, and that's another application of what's going on with changes in the muscle geometry throughout the range of motion. All right, mechanical work. W. W equals force times distance. So here, if we move this curve for 20 feet, that will be here 20 feet. And if the force is 100 pounds that we have to apply, what's the work? It will be 100 pounds times 20. So the work will be 2,000 pounds per feet times 3. So it's 2,000. Okay. If I move this for 10 feet, that will, 10 feet, right? And the force is the same, what's the work? 100 pounds, 10 feet. That will be 1,000. 30 feet, 3,000. If I move it for the same distance with more force, I will produce more work, right? Let's see why we care about work. And this is one of the second cases that you may pick, right? One was the first sticking point, and here we'll have some different routines, and we're trying to see work. Okay, so here we have a strength routine, more load, more weight is going on, less reps, same sets, same displacement. Which one will produce more work? That's for you to prove to me. I want to see those calculations and I want to see some explanation. Okay. All right. All right. Have you ever heard of negatives? Is there negative work? Well, technically, there's no negative work, right? Work is always positive. There's work happening. But why do we call it, as you can see here, negative work with that emphasis? Okay. So let's say here, we see the force of contraction, right? It's going this way, and then you have 10 pounds here, and then the direction of the movement, flexion is going this way. So when we move, when the direction of the movement and the direction of the force of contraction are going the same way, then we're talking about positive work or work. Here, this is a negative. The force of contraction is going this way, okay, but the movement is going this way. So I'm trying to contract and I'm contracting, but it's too heavy and it's just going the other way, although I'm trying to pull this way. So the force of contraction is still this way, but the movement is going that way. Opposite directions, that's called negative, okay? A lot of people do negatives, for example, with bench press, right? Somebody's giving the bar to you, lift off, right? And then slowly it moves down, right? And most likely that same person will pull it up and then you do the same thing. And negative work is very important for other reasons, for example, in bodybuilding, because it creates more muscle destruction and that's good for hypertrophy. But what I want to remember here is that we have that positive work. And although it's always work is positive, we call this negative because this direction is opposite to this direction. Good? All right. This is the third case that you may pick. We have some variables involved. There's a common factor which will lead you to the answer. Okay, the common factor. That's the hint here. All right, power for rotational movements. And in this case, a lot of times we use, wheelchair propulsion, and we have athletes that they're doing it. There are all kinds of sports that have wheelchairs and even participate in the Olympics. So here, since we talk about power, okay, and the angular power, because now we have rotation going on, of course, it will equal the angular moment times the angular velocity. Everything is angular. We have rotation. And as you can see here we have speed, velocity. Here we have rotation, internal rotation. So internal rotation, and then we'll have external rotation muscles. So why am I showing you this? I'm showing you this because if we divide these things, we get an R. This is the ratio of internal, external, isokinetic, shoulder rotation, mean power. The faster they go, the higher the ratio, which means more internal rotation. More internal rotation, less external rotation creates a muscular imbalance, and that creates issues always, right? So as a coach, as a trainer, you need to know that and trying to activate with maybe some supplemental exercises, the external rotation muscles, so you can avoid that imbalance. All right, another thing that's important, we have muscle force. And in other chapters, we're going to talk about the slide filament theory. The active muscle force happens based on that theory, okay? The actual activation of the muscle. Now, we also have passive muscle force, and that has to do with elastic force that is getting stored in the muscle as we stretch it or pre-stretch it, okay? And I want to ask you, if you want to jump and try to touch the ceiling, are you going to bend your knees a little bit and jump, or just jump from an upright position? I'm guessing you're going to just bend your knees a little bit and then jump. Why? Well, because you're taking advantage of the passive muscle force that comes from pre-stretching the muscle, which produces elastic force because the muscle, like a band, if you stretch it and then you release it, then it will try to come back to its original position or length, right? And that is force, elastic force that we can take advantage of. Yes? Okay. And then let's talk about the length tension relationship. Our muscles, let's say my bicep, right, are already a little bit pre-stretched, and they're attached here and here. Okay, they're a little bit pre-stretched. And they have the optimal length to produce the most force. Not very stretched, not too close to each other, because we're going to explain how the sliding filament theory works later on. But just remember that it's already a little bit pre-stretched, because if I, knock on wood, I cut my bicep, will come all the way up, right? So they're a little bit pre-stretched, touched with our tendons to the bones, and that's the optimal length to produce the most force. Now, if you see it this way, you see that when we talk about active tension, this is the resting length, and at the resting length, we can produce the most tension. Yes? Okay. Passive tension, as we said, as we start pre-stretching the muscle, which means increasing the length, right? We produce more and more tension. That's called passive. Now, you see that we can produce the most tension if we put them together. So if we put them together, the total tension is higher at an elongated position, as we say here, because that's how we put them together. And that's a perfect example. This guy here is trying to jump as high as possible. And you know how this test works. If it doesn't, you just jump and you move as many as you can, and and from that you can calculate how high he jumped. Pretty classic for, let's say, volleyball and basketball. All right, but you see this guy here, he's pre-stretching his muscles before you're doing it, before jumping. He's not jumping from an upright position because he wants to take advantage of that passive tension. Okay, again, the muscle is like a band. If you pre-stretch it, there's elastic force that's stored there, and then boom. Okay, and that's exactly what he's doing. I hope that makes sense. Another application of what we said, I'm sure you heard before, that this is the right way to lift an object, bring it close, and use your legs, right? What's going on here? We have the moment arm here, which is 2 feet from the pivot point. So if we're trying to calculate how much effort we need, we have to multiply 2 feet times 100. That would be 200. Here, if we move it closer, same load, same weight, but this is like 1 foot, it's 100. So the same load, the same weight, the same object, if we lift it this way, it feels lighter. It requires less effort. This is a position that will have more effort and puts a lot of stress right here. That's why we say this is not the proper way to do it. This is the proper way to do it. The moment arm here makes all the difference. I don't want to talk about gait a lot. We have kines, but if you pay attention to the right leg, you can see Now we have two phases, the stand phase and the swing phase, right? Most of it is the stance phase. And when we're walking, there's one thing that's not happening when which happens when we're running, which is the flight phase. Here, the foot is always in contact with the floor, one of the feet. That's what I mean. That's all I want from here. This is some gait abnormalities and how they look like and what we should do. Nothing that I want to pay too much attention. I'm going to read the take-home points, and that will be for me for this week. Biomechanics is the branch of science that applies the principles of mechanics to living organisms. An understanding of biomechanics provides a great advantage to the personal trainer, as this understanding provides the framework for viewing the human body in terms of a lever system acted on by forces internally by the muscles and externally by interaction with the environment. Because levers rotate around an axis, forces imposed on the human body create torque or moments, when forces are magnified by the length of these levers. I'm going to stop sharing the slideshow. This is all for me. Let me know if you need anything tomorrow, office hours, Wednesday, our synchronous meeting. In the meantime, lift intentionally, not habitually. Bye, guys.